This conference will now be recorded.
Hello everyone. So we'll start with problem, and then we'll also see chemical properties of carboxylic acid. So the question is saying that what is the correct order of acidity of the following? Here we have total 3 acid: acetic acid, acrylic acid, and propionic acid. And in different options A, B, C, D, we have different orders for these 3 acid for their acidity. So acetic acid structure is very simple: CH3COOH. But when it is acrylic acid, what is the structure? And when it is propionic acid, what is the structure? That we have to know. So these two are the structure of acrylic acid and propionic acid. So this is acrylic acid and this is propionic acid. Okay. Now try to understand the difference. Acetic acid, CO2H group, CO2H group and CO2H group. So keeping this part common, if we look at the other part of the molecule, in case of acetic acid, we have methyl group. In case of propionic acid, we have this CC triple bond. And in case of acrylic acid, we have CC double bond. Now, the carbon with which the carbonyl carbon of carboxylic acid is attached, we have to focus to that carbon. So here, this is the carbon with which carboxylic acid carbon is attached. In this case, this is the carbon which is sp2 hybridized. And in case of propionic acid, sp hybridized carbon is attached to CO2H carbon. So it means what? sp hybridization, here 50% S character present. In this case, it is 33.3%, and here it is sp3 hybridized. That means here it is 25%. Now, higher is the S character, higher will be the electron withdrawing property. So that is why in case of propionic acid, this carbon will be maximum electron deficient. That means sp hybridized carbon, it will draw electron density towards this side, towards its side. Okay, so that is why hydrogen, its acidity, if we consider, maximum acidity will be for this hydrogen, propionic acid hydrogen. After that, acrylic acid, and then it is acetic acid. So if we follow this order, it will be this option, that is option C. Fine. Next question is saying, if the pKa value of acetic acid is 4.76, pKa value means negative logarithm of Ka value, acid dissociation constant. If this value is 4.76 for acetic acid, we have to predict the pKa value of HCl. Fine. Now HCl is inorganic acid, that is mineral acid, and we know that carboxylic acid, if you consider inorganic compounds, obviously its acidity is very high. But it is not so acidic as that of mineral acids of that are found in inorganic chemistry. I mean to say H2SO4, HCl, HBl like this. So that is why obviously now acidity will be high in case of HCl. And when acidity high, Ka value is high. And when Ka value is high, pK value is less, because pK is nothing but negative logarithm of K. So there is a negative sign before log K. That is why inverse relationship. So if pK value for acetic acid is 4.76 and HCl is having higher acidity, it must be lesser than this value. Okay. Now, if we see lesser value, two values are there. One is 4.2, another one is -7. Now, among these two, which one to choose? How we will know that? Basically, if you choose 4.2, it is true that it is less, but it is not so less. But if you choose -7, it is actually very less. And this is the correct answer, because HCl is, if we compare its acidity with respect to acetic acid, it is highly different. So here, see what is written. Generally, carboxylic acids are weaker acid than the mineral acids like HCl. Also, mineral acids are very strong acid, that is HCl, HNO3, H2SO4, and their pK values usually less than 1. Fine. So less than 1 means obviously one option is correct, which is -7. Okay. So this should be the correct option. pK value. Be very careful, read the question carefully, whether it is asking for pK or pH or K, that you have to read carefully. So it is asking for pK, So it will be very, very negative. More negative is pKa value, or you can say lesser is the value of pKa, higher is the acidity. The correct order of acidity of the following compounds. So following compounds, one thing is common, all are basically benzoic acid derivative. Benzoic acid is benzene ring and CO2H group directly attached to it. But when I'm saying derivative, there must be some other substituent. So here you can see we have OH substituent and different OH substituent. That is, in case of first one 2 OH, in case of second one 1 OH. Then position of OH is changing 2 to 3 to 4. It is ortho, meta, and then para. So we have to find the correct order of acidity. Now one thing before starting the discussion, we have to know that there is one term which is known as ortho effect. What is ortho effect? It is observed that the ortho substituted benzoic acids, they are considerably stronger acid than the benzoic acid. If you compare benzoic acid, simply PaCO2H, and ortho substituted, not just OH, if you consider any other substituent, you will see there is always higher acidity. I'm talking about when it is ortho substituted, it is always higher acidity. Irrespective of the fact whether the group that is present at ortho position, whether it is electron donating group or withdrawing group. There is one exception also. So this is the observation. Fine. Now what is the reason behind it? That is explanation behind it. That is not completely understood. But explanation is you can give in terms of steric or electronic factors. Okay. So if we keep this fact in mind, obviously 1 and 2, that should be having more acidity compared to 3 and 4. Now 1 and 2 having higher acidity compared to 3 and 4. That is, I'm combining these two because we still don't know whether 1 is more acidic or 2. But suppose these two, we can, from this ortho effect, we can easily say, obviously it will be more acidic than 3 and 4. So this much information, just try to see whether it is enough to choose the correct option. 1 and 2 before 3 and 4, it is present only in option 1, isn't it? Because if you look at option 2, 1 and 3, then 3, 4, 1, 3. No, it is not like that. So this much information is enough. You can easily choose option 1. Okay. Now we will see separately why it is so. 2 will be more acidic compared to 3 and 4. But why 1 is more acidic compared to 2? That we can see. So when there are 2 OH group, both sides, what will happen? Because of steric problem, this CO2H group will be out of plane. That means the benzene ring, if it is on the plane of this laptop, okay, wherever you are watching, if this benzene ring, it is on the plane of the laptop, then CO2H will be perpendicular to it. Now when CO2H is perpendicular, then resonance with the double bonds of benzene ring is not possible. So suppose if CO2H group, it is in the same plane of benzene ring, then this type of resonance is possible. So as a result, what you are getting? Positive charge, double bond, CO minus OH. Okay. But suppose if this type of resonance with the double bonds of benzene ring is not happening, in that case, another type of resonance is also possible, which is resonance with the lone pair of this OH group. So this is another type of resonance that is possible without disturbing the double bonds of the benzene ring. Now this oxygen is positive. That means the H, which is actually the important fact, that is whether this hydrogen is acidic or not. That is actually important because this hydrogen is actually lost when you consider dissociation. Now this hydrogen is very acidic because now the oxygen with which it is attached, this is positively charged. Now this type of resonance is only possible when the double bonds of benzene ring is not taking part in resonance, and that is possible in case of the first compound because of these two ortho substituted, that is ortho substitution, CO2H group will be out of plane. Now this type of resonance that I have shown just in blue color, that will be possible, and because of that the acidity of this hydrogen will be very high. Okay, so that is why 2 is more acidic compared to, sorry, 1 is more acidic compared to 2. But if you want to know why ortho-substituted compounds are always more acidic than meta or para, then this reason also you can apply, that even if it is one ortho-substitution, but still there will be some steric problem compared to meta and para. And because of that, in some molecules CO2H may be out of plane. And this type of resonance that is shown in blue color is possible. As a result, acidity will be very high. Okay, so in this way we can give the explanation that why ortho effect is operating, and not just ortho effect. If you have mono ortho and diortho, then also you can give the explanation why the diortho is more acidic, because now it will be completely out of plane. So based on all this, we can choose the correct option, which is the first option. Now we will start chemical properties of carboxylic acid. So when I'm saying carboxylic acid, just try to remember its general structure, RC double bond O, OH. So if this is the structure, then based on which part is actually taking part in chemical reaction, based on that we can make some categories. They do not give characteristic reaction of C double bond O group that you can observe in case of aldehyde and ketone. Why? Because now you also have OH group, and because of this OH group, this C double bond O, it is not behaving in a similar way that you can expect in case of aldehyde and ketones. So that is why now it will be giving some different type of reaction, and here we have 4 categories. The first is salt formation. Now when we are considering salt formation reaction, obviously this H will be replaced by some metal, and this is basically its acidic property. Next type of reaction is possible where this OH group is replaced by some other group. That means this carbon-oxygen bond will be broken. Third type of reaction is possible when the total group, that is both C double bond O as well as OH together, is taking part in reaction. Then this is the third category. And the fourth category is when this hydrocarbon part, I mean this alkyl part, not just alkyl, it may be benzene ring also, but whatever it is, when you are having any reaction in this hydrocarbon part, alkyl part or benzene ring part, then there will be 4th category of reaction. Okay, so we'll start from A, type A. So it is reaction with metals. They can react with active metals such as sodium, which is from group 1 S block, magnesium group 2 S block, zinc it is from D block, right? And it can form corresponding salt, and also there is liberation of hydrogen. So let's see the examples. 2 acetic acid molecules reacting with 2 sodium. Now why we have taken it 2 times? Because for each acetic acid and each sodium there is 1 H removed. So 2 H when removed, you are getting 1 H2. You can also put it here 1 1. In that case it will be half hydrogen. Okay, so just to so that you don't have to add any half hydrogen, so you can also write this equation, that is balanced equation. So what we are getting ultimately, sodium acetate and hydrogen gas. Similarly, you can also take zinc. Now you don't have to take 2 zinc. 2 acetic acid molecule, 1 zinc is enough because zinc is divalent. So now this is the formula for zinc acetate. Part zinc, 2 CH3COO, that is acetate ion will be both sides, and plus hydrogen gas liberated. Then reaction with alkalis and bases. So see, under salt formation, the first reaction is reaction with metals in blue color. Now the second point under same type of reaction is how it is reacting with alkalis or bases. The previous question you have seen how it is reacting with metals, but now you are seeing how it is reacting with bases or alkalis. So when I am saying alkali, that means alkali metal hydroxide, or it may be any other type of base. For example, it may be amine, simple amine, that is ammonia. Then the resulting salts that will be produced, it is ionic in character, and that is why it is soluble. So see, acetic acid reacting with this alkali NaOH, you are again getting sodium acetate, but now not hydrogen, you are getting water. And then heavy metals such as silver, mercury, lead, they can form salts having more covalent character. So compared to sodium, potassium that are from S block, if you take this type of metals, that is heavy metals I'm talking about, then the metal salt that you are getting compared to the previous type of salt, now it will be having more covalent character. As a result, water solubility is not so high that you have seen in case of sodium acid, especially for acid composed of 4 or more carbon. If it is lesser than 4, 3, 2, it is still will have some solubility, but if it is more than 4, then solubility will further decrease. So here we have taken not directly silver, but silver hydroxide. You can compare it with sodium hydroxide. This is also hydroxide. So what you are getting? You are getting RCO2Ag. It is same as the that is formula CH3COONA. Again water. Now we have taken tertiary amine, the trimethylamine. So tertiary methyl when we have taken, now this H is removed, so it is RCO2 minus and protonated trimethylamine. For this anion and cation, they will stay together because of this electrostatic interaction. Fine. But instead of taking Me3N, if you take ammonia, which is that is 3 hydrogens, not 3 alkyl group, then what will be the reaction? We will also see in some other category. Number 3. So all these reactions that we are discussing, 1, 2, 3, that is related to acidic property, or we can say it is a kind of salt formation. Third type is how it reacts with carbonates or bicarbonate. Now this reaction is also used for identification of CO2H group. Suppose you have any unknown sample and you want to know whether CO2H group is present or not. So then you can do this test, because in this test there is some generation of effervescence. Effervescence means some CO2 gas will be evolved, which is basically evolving from CO2H, and that is the reason, sorry, not CO2H, it is actually from this carbonate and bicarbonate, and because of this evolution of CO2 there is some effervescence, which is basically will help you to understand whether CO2H group is present or not. You can distinguish carboxylic acid and from phenol, because phenol, though it is acidic, but it is not so acidic that it can give this type of taste. So you can differentiate these two types of compounds. Acetic acid reacting with sodium carbonate, it is producing ONA. So here CO2 that is generated, it is not generated from CO2H, it is generated from this carbonate ion. And if you take sodium bicarbonate, then also same type of sodium salt is produced and CO2 is evolved. Remember, now this is from this part, it is coming from this part. So we will see this problem when propionic acid is treated with aqueous sodium bicarbonate. That is, you are treating it with NaHCO3. CO2 is liberated. The carbon of CO2 comes from. Now this thing I have just said that CO2 is basically generated from the salt that you are using. It is not generated from the CO2H group. And also remember, we are discussing this reaction under salt formation type. So when it is salt formation, only the H of CO2H group is taking part. It is not that the whole CO2H group is taking part. Fine. So if this is true, obviously this carbon is not coming from methyl group. Propionic acid means, prop means 3 carbon, CH3, CH2, COOH. So it is coming from methyl group. That means this carbon. No, that is not possible at all. This is a hydrocarbon part. Carboxylic acid group. This CO is also not the source of CO2 that is involved. Methylene group. Methylene group means CH2. So this CH2 carbon is also not the source of CO2, but bicarbonate. So this CO2 is basically coming from this carbonate. Fine. So this is the correct option. Now the second type, reaction involving cleavage of COH bond. So when it is cleavage of COH bond, that means, just consider the structure. This OH will take part in reaction. The first reaction we have, if you treat carboxylic acid with this type of reagent, PCl5, PCl3, phosphorus trichloride, pentachloride, thionyl fluoride, what will happen? Now the OH group, sorry, there will be no gap. The OH group of carboxylic acid behaves like that of alcoholic group. So as if now it is behaving, the structure is like ROH. So the reaction that you can expect from alcohol, when you are treating alcohol with VCl5, 3 or SOCl2, what do you expect? This ROH will be converted to RCl. So same reaction also you can expect here. Now among this reagent, SOCl2 is better reagent because here the byproducts that are formed both are gaseous in nature, and as a result you can easily purify the actual desired product. Acetic acid reaction with PCl5, OH is replaced by Cl, and the PET of PCl5 it is converted to PCOCl3 and ACl is generated. So here the byproducts are POCl3 and ACl, only this is gaseous. But when it is SOCl2, the byproducts are SO2 and ACl, both are gaseous, and as a result they can easily escape from the reaction mixture. So you don't have to bother so much about the purification of benzoyl chloride. So this is benzoyl chloride, PHCOCl. Remember, when it is PHCH2Cl, it is benzyl, ZYL. When it is PHCOCl, it is benzoyl, ZOYL. Formation of anhydride. When you treat carboxylic acid, two molecules of carboxylic acid with mineral acid such as the which is having some dehydrating property, it can help in removal of water molecule, or you can also treat it with P2O5. So here our purpose is just to remove water molecule in this fashion. So we are removing basically OH of one RCO2H and H of another RCO2H. So you can think that why we are discussing this in category type B, because only if you consider this molecule, then it is reaction involving OH, but if you consider the other molecule, it is actually only one H. But whatever category we have kept this reaction, that is not important, just have to understand the reaction. So OH and H is removed. As a result, this carbon and the oxygen, this oxygen, there is bond formation. So this is a newly generated bond and water molecule is removed. So if you take same molecules, that is two carboxylic acid molecules, both are same, it will be like this, both sides are R. But if you have taken different, it may be R point like this. In that case, the anhydride is called mixed anhydride. Reaction with alcohols, that is reaction of carboxylic acid with alcohols, which is also known as esterification, because here the product that is produced, that is actually ester. In this reaction, what we use, that is obviously we have to use alcohol, but in presence of concentrated H2SO4 or dry HCl gas. Now this is benzoic acid, PaCOOH, and we have taken ethyl alcohol. Here one important thing, notice this oxygen is labeled. That means this is not 16 isotope of oxygen, it is 18 oxygen. But why we have done so? So that you can understand, after reaction, this oxygen, is it coming from benzoic acid or it is coming from alcohol? So as it is already labeled here, it is clear and it is still present in the product. So it means this OH and this H is removed in the form of water because this 18 oxygen is still there. So this is called labeling experiment, so that you can understand what is the source of this oxygen. Fine. So general structure of ester is RC double bond O, OR prime. So here R prime is ethyl group, this R is phenyl. If we see the mechanism, first carboxylic acid in presence of H plus, it is protonated. So this lone pair, it will be attracted towards proton. Next, the alcohol molecule, the lone pair over the oxygen, that lone pair will act as if it is nucleophile. And now this OH is neutral and this oxygen of alcohol is protonated, it is positively charged. And this is tetrahedral, it is called tetrahedral intermediate. Now there will be proton transfer. So this H, if it is transferred to this OH, now this will be OH2 plus. This oxygen is neutral again. Under this condition, one water molecule can be removed. When this lone pair, it is making a double bond between carbon and oxygen, this carbon oxygen bond will be broken. We are getting protonated ester, and finally this proton is removed, we are getting actual product molecule. Number 4 reaction. Reaction with ammonia. Remember, in the first category of reaction, that is type A, you have seen how carboxylic acid is reacting with trimethylamine, which is tertiary. Okay, but just remove all the alkyl group. Now if you take H, now the reaction is different. So when it is ammonia, first there will be formation of ammonium carboxylate. So up to this point, it is the same observation that you have seen when you have taken carboxylic acid and Me3N. Remember, O minus and N Me3, as it is protonated, now positively charged nitrogen. So same thing is also happening here. Now NH3 is protonated, it is NH4 plus. But this is not end of the reaction. If you further heat it, now you are getting completely different type of product, which is not possible in case of tertiary amine. Now you are getting amide. So if in any problem it is mentioned that first R's carboxylic acid is heated, sorry, it is treated with ammonia, then you are getting some product. And then it is again, there is a heat sign. That means the final product should be amide. Similarly, instead of taking ammonia, if you have taken some primary amine means with nitrogen there is one alkyl group, two hydrogen. In this case, what will be produced? Obviously, this type of salt can be generated, but ultimately, if you heat it, there will be NHR prime. So when it is ammonia, it is NH2. When it is R prime NH2, it is NHR. Okay. So this is also amide. This is 1 degree amide. This is 7 degree or 2 degree amide. Related problem. The product D of the reaction. So look at the reaction. First, you have taken methyl chloride. You are treating it with KCN. So what will be produced? There will be formation of CH3CN. The simple substitution of Cl by Cn, where Cn is the nucleophile. Then you are hydrolyzing. So CH3CN, that will be converted to CH3COOH. Then this is B. You are treating it with ammonia. Remember what we have seen? When first you treat it with ammonia, there is formation of CH3CO O minus NH4 plus, ammonium salt of carboxylic acid, but there is heat sign also. This is not the end product. So when you heat it, ultimately it will be amide. So which option should be correct? This option. The product D, in the following sequence of reaction, we have to find. First, acetic acid treated with ammonia. A is nothing but this molecule, ammonium acetate. Then heat. That means B is CH3CONH2. So this is actually B. I'm just writing from this P2O5. Now P2O5 is basically dehydrating agent. So there will be removal of water. Now when removal of water I'm saying, that means if you heat amide with some dehydrating agent, basically this oxygen and H2 is removed. So as a result you get CH3C triple bond N. So this is basically D. But finally you are using, sorry, this is C, not D. D is the final product. C is now treated with sodium ethanol. Now sodium ethanol is basically reducing agent which helps to reduce this CH3CN. So reduction sign I am writing H within third bracket, and ultimately if you reduce that is cyanide, it will be CH2. Hydrogen will be added, NH2. So total 4 hydrogens are added. So this source of hydrogen is coming basically from ethanol. So ultimately you are getting what? Amine type of molecule. So it is not ester, it is not acid, it is amine. Option B. Alcohol also not correct. Category number C. Reaction involving carboxylic acid group. The first reaction under this category will see reduction. Now, if you consider oxidation state of carboxylic acid group, it is basically towards higher side. Look at these molecules that are written carbon dioxide. Here oxidation state of carbon, it is +4. Reason is it is having total 4 bonds with oxygen. So for each oxygen, if we consider oxygen is more electronegative than carbon. So for each CO bond, you have to consider +1 charge for carbon. Total 4 bonds, so it is +4. When it is formic acid, now we have total 3 CO bond, right? That means +3 for carbon, but we also have hydrogen. Now when it is hydrogen, you have to consider negative charge over carbon, so that is why 1 CH bond, for that it will be -1. So +3 -1, it will be ultimately +2. In this way you can easily understand what will be the oxidation state of carbon in different organic molecules. So when it is formaldehyde, you have 2 CO bond and 2 CH bond. That means it is cancelling each other, so it is 0. Similarly, here we have 3, in case of methanol, 3 carbon hydrogen bond, that means -3, and 1 carbon oxygen, +1, -3 +1 -2. And similarly for methane, oxidation state is -4. So what we are seeing, when it is formic acid, it is basically +3. But instead of taking formic acid, if you take any other alkyl group containing carboxylic acid, suppose this R is methyl or ethyl, in that case you have CC bond here, right? So for CC bond we will do not consider any oxidation state because it is bond between the same atom. But we have 3 carbon oxygen bond, so for 3 carbon oxygen bond it should have +3. So for carboxylic acid, only for formic acid it is +2, but for other carboxylic acid except formic acid, it will be always +3 when there is carbon-carbon bond present. So it is relatively high oxidation state, because you can see in other compounds it is 0, -2, -4. Only carbon dioxide, it is higher than, even higher than carboxylic acid, but +3 is also quite high. Now if it is high, then reduction to 1 degree alcohol takes place rapidly because it is already in high oxidation state. Reduction to 1 degree alcohol takes place rapidly if you are treating it with powerful metal hydride reagent. Hydride means source of H minus. So H minus will be the actual reducing agent, but that will be generated from lithium aluminium hydride. That is one reagent you can use, very reactive reagent, or you can use H2 in presence of copper chromite, Cu2Cr2O5 as catalyst. So what, and also B2H6. So what we have seen here, You can use lithium aluminium hydride, number 1. You can use H2 in presence of copper chloride, number 2, where copper chromate is the catalyst, or number 3, you can use B2H6. So this is the general equation for reduction to alcohol. So I am written here partial reduction. Why it is partial reduction? Because further reduction is also possible. We'll come to that point. Right now, just see, it is basically addition of total 4 hydrogen and water is also produced. So 1 oxygen will still be here, another oxygen and 2 hydrogen, it will make H2O, and there are 3 hydrogen. So we are getting 1 degree alcohol. This is 1 degree alcohol. And for this, you can use any of this reagent. This is the general equation. You can also consider these equations. You are using lithium aluminium hydride, and after that you have to do acidic workup. So this C double bond is converted to CH2. Then you can also use copper chromate hydrogen gas. This is the full structure of copper chromate, Cu2Cr2O5. See, okay, and you are getting 1 degree alcohol. You can also use BH3.THF. Basically, it is nothing but B2H6. It remains in dimeric form. So whether you write it as BH3.THF, THF means tetrahydrofuel, ether. It makes complex with ether molecule. That is why it is written in this format. You can also write the dimeric form. So these are the 3 different reagents you can use. Now diborane, here there is one unique property. If you use diborane, it does not easily reduce functional groups such as this. So as a result, what I'm trying to say, if in the carboxylic acid molecule, suppose except CO2H group, there is also some other groups like this. But you want to reduce only CO2H group. So in that case, it is very good reagent, B2H, because it will selectively reduce only CO2H, which is our purpose. But it will not reduce the other groups. Other groups will remain intact. And for carboxylic acid, you cannot use NaBH4, sodium borohydride, because that is not so strong reducing agent. It can reduce, you can use it for aldehyde, fine, but not for RCO2H. Okay. Most suitable reagent for the given conversion. So here, if this is starting material and this is product, in the starting material we have CO2H, amide, ketone, CN. But if you look at the product, ketone intact, amide intact, CN intact, but not CO2H. So it is only the conversion of COOH to CH2OH, which is 1 degree alcohol. Rest of the groups should not be disturbed. So obviously you cannot use lithium aluminium hydride because it is very strong reagent. It will reduce all the other groups. And NaBH4 is so weak, it cannot reduce CO2H. Then H2PT, this is also not suitable. And B2H6. So B2H6 actually will be correct answer. So see the problem with other reagent 1, 2, 3. LiAlH4, it would reduce all the groups. It is very strong reagent. NaBH4, it can reduce only ketone, but we don't want ketone to be reduced. Then PTH2, it will reduce only nitrile group, that is CN, but CN is intact, there is no change. Diborane is the only reagent which can selectively reduce only CO2H in presence of some other groups. Okay, ketone ester or CN. So that is why this should be the correct option. So number 1 point we have seen partial reduction to alcohol, but if you do it completely, then it will be converted to alkane, not alcohol. Okay, because when it is alkane, if you consider the oxidation state of carbon, and when it is alcohol, then also consider the oxidation state. You will see, just follow the same method that we have used here in the first 5 molecules, how to find out oxidation state. So obviously in case of methanol also you can see it is -2 oxidation state of carbon, but when it is alkane, it is even more negative, -4. So obviously conversion from +3, which is the oxidation state of carbon in carboxylic acid, +3 to -2 and +3 to +4. Obviously, in the second case, +3 to -4, that is complete reduction. So when what we have to use for this purpose, we have to treat carboxylic acid with hydroiodic acid and red phosphorus. So in this presence of in this reagent, carboxylic acid undergoes complete reduction, it forms alkane, and there is no loss of carbon. So see, HI in presence of red phosphorus, temperature 473, we are getting ethane. So here we have 2 carbon, this is also 2 carbon. Okay. So number 1 and 2, that is partial reduction, complete reduction, we have seen under reduction type of reaction, which is number 1 in blue color. Then now we are seeing decarboxylation, second type of reaction. Now decarboxylation may be different types. Sometimes we simply use heat for decarboxylation. Sometimes we maybe use some reagent. So see, this decarboxylation is we are not using any reagent, it is simply we are heating the carboxylic acid. Decarboxylation reaction is defined as the chemical reaction where CO2 is removed. So that is why the name decarboxylation, removal of carbon dioxide. You have taken carboxylic acid, this part is removed. So you are now left with R and H, right? So this is the general way by equation for decarboxylation. The simple aliphatic carboxylic acid, suppose the carboxylic acid, it is simple aliphatic, that is CH3CO2H or propanoic acid. Then what will happen? They do not lose CO2 if you simply heat it. But suppose if there is any strongly electron withdrawing group attached to alpha carbon, that is with respect to CO2H alpha carbon, if there is an electron withdrawing group, then decarboxylation is possible in this temperature range. Fine. So we will see some examples. Here we have, see, this CO2H group, if you consider is carboxylic group, this is the alpha carbon, and in alpha carbon we have this electron withdrawing group, which is basically another CO2H, but it is electron withdrawing group. Then this alpha carbon, there are 3 chlorine. This is alpha carbon, there is NO2 group, which is very electron withdrawing. Then we have CH3CO group in this alpha position, we have CN in this alpha position. So for all these type of molecules, okay, we and also have 2,4,6 trinitrobenzoic acid, though it is not possible that in alpha carbon there will be anything, but still this NO2 group, it can play their electron withdrawing effect. As a result, decarboxylation is possible. Fine. So these are some of the examples where you can see electron withdrawing groups are present, and if you heat it in this temperature range 100 to 150 degree centigrade, decarboxylation is possible. So here we have taken this molecule, the mechanism of thermal decarboxylation, as we are using only heat, so this is thermal decarboxylation. Probably the mechanism for this type of thermal decarboxylation, it is not same, there is no general mechanism. But suppose if there is any double bonded functional group such as C double bond O, C double bond N, C double bond O double bond N, or CC double bond, then you can have some mechanism which is cyclic elimination process. That means the intermediate, it will have some cyclic nature. So here we can see, if you look at this example, this is the carbon with which CO2H group attached. So this is alpha carbon, and with alpha carbon you also have this double bond. Fine. And this is also beta keto acid, because at beta position there is keto group. Now you can, if you follow these pink arrows, what you will find? You will find that there is removal of this part. This H is attached to oxygen, and there is a double bond in this, sorry, in this position. Okay, so you are basically getting enol type of structure. This is within third bracket, there will be tautomerization. Ultimately you will be getting C double bond O and H will be here. So finally you are getting cyclohexanol if this is the starting material. And we also have this molecule. Now it is true that this is CC bond, double bond attached to CH2, but this is not exactly very good electron withdrawing group. So that is why heat is to some extent high, greater than 200. Fine. So here also, if I write it in this way, CC double bond, then CH2 OH, C double bond O. So same molecule I have written in this way. Now this type of mechanism you can follow. OH bond broken, this CC bond is broken, and there is a newly generated CC bond in this position. So what you are getting? You are getting molecule like this, which is nothing but this one. CH2 double bond CH3, and CO2 is removed, this part. Then another molecule. So suppose you have taken CO2H, then CH2, then in another CO2H, and if you write the molecule in this fashion, okay, so here this C double bond O, pi bond broken, this OH bond will be formed, this OH bond will be broken, this will be removed in the form of CO2. This is the newly generated CC bond. So this is basically enol form of ethanoic acid. If you tautomerization is going on, then C double bond O will be formed. This CC double bond is broken. We are getting HO, CO, CH3, which is nothing but acetic acid, and CO2 is already removed. Fine. So these are the examples of thermal decarboxylation. Number 3, decarboxylation by using soda lime. Soda lime is mixture of NaOH and calcium oxide in this ratio. In this case also CO2 is removed, but here starting material is sodium salt, which is, as you are using NaOH CO mixture, so obviously in presence of NaOH it will be converted to ONA, and CO is also there. We are getting this part will be removed, remember, and it will be converted to CH4. You can also follow this general equation, this one. So basically in general, any decarboxylation, whether it is thermal or you are using some reagent, whatever it is always removal of this part, these R and H together, now it is RH. So that is why this CH3 and H together, it will be CH4, and this is the byproduct. So using this mixture of sodium hydroxide and calcium oxide also, which is also known as soda lime, we can have this type of reaction. How many of the following can undergo decarboxylation on heating? So here we have 1, 2, 3, 4, 5, 6, 7, 8. So it is mentioned decarboxylation using only heat, right? So remember, if there is any electron withdrawing group or CC double bond, CN double bond, C double bond O at the alpha position of CO2H group, then this thermal decarboxylation is possible. So if you look at the first compound, this is alpha carbon, because with this carbon CO2H group is attached, and with alpha carbon CC double bond is also present. So thermal decarboxylation is possible here. Next compound, this is alpha. Now with alpha there is no direct electron withdrawing group, so this will not give reaction. Then we have number 3, alpha position, we have this electron withdrawing group. Number 4, this is alpha. Now with alpha we don't have any direct group, right? Then number 5, alpha. Now with alpha we have C double bond O. And also remember, for any beta keto acid, decarboxylation is possible, thermal decarboxylation. Beta position keto group and it is acid. But with respect to acid, at beta position you have keto, so name is beta keto acid. Then this is alpha, and with alpha we have electron withdrawing group, so this will also give thermal decarboxylation reaction. Then for number 7 compound, with respect to alpha position, there is electron withdrawing group, both side. Then number 8, alpha, but with alpha no direct electron withdrawing group. So among these 8 compounds, these are the compounds where thermal decarboxylation is possible. So this is actually beta keto acid, which is number 3 molecule given in the question. This is also beta keto acid, which is basically number 5. This is number 7. This is number 1. So this is beta gamma unsaturated acid, because with respect to CO2H group, this is alpha, this is beta, and this is gamma. So at beta and gamma position you have CC double bond. So this is also, you can say it is beta gamma unsaturated acid. Then 1,3 dicarboxylic acid, 1 position, 2 position, 3 position. So this molecule is basically number 6. So among these 8 molecules, 3, 5, 7, 1 and 6, these 5 molecules can give thermal decarboxylation reaction. Out of 8, only 5. Another type of decarboxylation, which is known as Kolbe electrolysis. So we have to do some electrolysis. So see what we have done. Suppose you have taken sodium salt of any carboxylic acid in presence of water when we are doing electrolysis. As we have taken 2 molecules, so 2 are grouped together, it will make alkane. So the end product is alkane, and these are the byproducts. So this method involves electrolysis of sodium or potassium salt of carboxylic acid, in which carboxylate radicals are formed first. And how this radical is formed? Because of transfer of an electron from the carboxylate ion to the anode. So when it is carboxylate ion, there is fully developed negative charge, but if one electron is lost, there will be radical generation. Fine. So look at this mechanism. This is carboxylate ion. You can also say this is sodium salt of acetic acid. But if you remove one electron from this O minus, basically total 2 electron, because we have 2 acetate ion. So ultimately now there will be single electron. These 2 electrons are already there because of already 2 lone pair over oxygen present. But now this is, you can also write it as total 6 electron, but 1 electron is lost. Now it is like this. And finally, if this bond is broken, so there will be CH3 dot, another dot in this carbon. So this dot generated in this carbon, and there is already 1 odd electron. These 2 together will make bond. So it is now carbon dioxide. But we are getting 2 methyl free radical. These 2 methyl free radical together can make ethane molecule. Fine. So this is the reaction going on in anode. And at cathode, we know there is always reduction. So water molecule is accepting electron. Water molecule, if you consider in this way, so it is as if HO minus H plus. So if H plus is accepting 1 electron, now it will be H dot. HO minus is still there. 2 H dot together, it is H2, right? That means now at cathode there is hydroxide ion, and at anode there is already sodium salt, and 2 acetate means 2 sodium. So sodium plus is already there at anode without any disturbance, and now they are at OH also. Basically it is 2OH minus. So ultimately you will also get the byproduct NaOH. So NaOH is generated, and CO2 is already generated in cathode. Hydrogen is generated in anode. Decarboxylation may occur simultaneously or subsequent to the formation of carboxylate radical. So this is carboxylate radical, from which you are getting hydrocarbon radical first. In our case, it is methyl radical, and these two methyl radical or any other alkyl group may be also there. They are subsequently dimerizing. Fine. So these are the mechanisms that are going on in anode, where it is basically oxidation, removal of electron, and cathode, the electron that is removed at anode, that electron is accepted by water. Ultimately, it is forming H dot, HO minus, 2 H dot together making H2. But our desired product, we are interested in this because that is actually the decarboxylation product. Fine. So we will end here. Another type of, we will discuss this Kolbe electrolysis problem the next class, and also there is another type of decarboxylation that also we have seen. And then we have the type D reaction, where the hydrocarbon part of carboxylic acid will take part in reaction. Okay, we will end the session here. Thank you for listening.